Welcome to this technical summary of a recent scientific study published in Colloids and Surfaces A. In this work, researchers investigate how surfactant solutions interact with We begin our detailed analysis with Figure 2, which plots the zero-frequency viscosity of surfactant solutions as a function of diclo concentration for multiple levels of CpYCl surfactant concentration. Each curve corresponds to a different surfactant concentration, as indicated in the legend. The zero-frequency viscosity, or eta zero, is extracted from the low-frequency plateau of the complex viscosity during frequency sweep tests. Remarkably, all the viscosity curves display a consistent general trend despite differences in surfactant concentration. As diclo concentration increases, the viscosity initially rises, reaching a peak that shifts to higher diclo concentrations for higher surfactant levels and grows in magnitude. After this peak, viscosity drops sharply. The authors distinguish three regions along this curve, which likely relate to micellar morphological transitions. The increase before the peak suggests micelle growth and network formation, while the decrease post-peak implies breakdown or transition to less viscous phases. The viscosity peak shifting with surfactant concentration indicates that the surfactant level modulates the interaction strength or micellar properties. Overall, the zero-frequency response reveals how charged drug addition alters structure and dynamics of surfactant-based micellar networks in a predictable manner. Next, Figure 3 illustrates the frequency sweep test performed on a sample with 5 millimolar CpYCl and 4 millimolar diclo concentration. This represents the lowest surfactant concentration studied. The frequency sweep reveals key viscoelastic characteristics typical of moderately entangled worm-like micelles. At low frequencies, the storage modulus G' and the loss modulus G" approach terminal region slopes of -2 and -1, respectively, on a log-log scale. Signatures of terminal flow behavior. As frequency increases, a first crossover occurs where G' surpasses G" and plateaus at a nearly constant plateau modulus G0. A further high-frequency crossover reflects micelle characteristic lengths. At very high frequencies, deviations occur likely due to inertial effects from the instrument or sample rather than fundamental material properties. The authors applied established models from Cates and Olschlager to extract parameters such as mean relaxation time, breaking and reforming times, reptation time, mean number of entanglements, and contour lengths of the micelles. These rheological measurements indicate that at low surfactant and drug concentrations, the micelles are long, stiff, and weakly entangled, consistent with the moderate elasticity observed. Such detailed characterization provides insight into the micellar dynamics and network structure, essential for understanding flow behavior. Figure 4 provides cryo-electron microscopy images supporting the rheology results for samples with 5 millimolar CpYCl at two diclo concentrations, 3.5 millimolar and 4.5 millimolar. Panel A shows entangled thread-like micelles at 3.5 millimolar diclo, characterized by long, low-density worm-like micellar chains with a cross-section around 2.4 nanometers, about twice the length of a surfactant tail. Overlapping micelles create multi-armed structures seen as dashed oval circles. Darker spots arise from folding or stacking of micellar chains along vitrophyte sample thickness. Panel E, at 4.5 millimolar diclo, shows a morphological transition. Vesicular structures appear with size heterogeneity amid a background of smaller micelles. This indicates a shift from worm-like micelles to vesicular aggregates. The authors hypothesize that the charged drug screens electrostatic repulsions, inducing folding and collapse of micellar chains leading to vesicle formation. Consistent with this, rheology shows Newtonian flow in panel B's composition, indicating loss of entangled networks. Hence, the microscopy visually confirms the drug concentration-driven micellar transformations suggested by viscosity changes and frequency responses, marking critical points for network formation and breakdown in these formulations. Figure 5 shifts focus to samples with higher CpYCl surfactant concentration at 16.7 millimolar, exploring diclo concentrations around the viscosity peak region, 10.0 10.5, and 11.5 millimolar. Panels A and B, representing diclo concentrations before and at the peak respectively, display rheological signatures characteristic of classical worm-like micellar systems. These features include terminal Maxwell slopes at low frequencies, a plateau region in the storage modulus G', accompanying a minimum in the loss modulus G" at intermediate frequencies, and a high-frequency crossover. Such behavior indicates a network of entangled cylindrical micelles with elastic and viscous features. At 11.5 millimolar diclo, panel C, above the viscosity peak, deviations appear at low-frequency slopes, but entangled network behavior persists at higher frequencies, pointing to formation of more complex microstructures. The samples at diclo concentrations outside this peak range exhibit simple Newtonian flow, suggesting no network. The viscoelastic data support a progression as salt concentration increases, from poorly entangled, rigid worm-like micelles through tighter entangled networks to branched micelles. This transformation mirrors morphological changes and reflects the influence of drug-induced screening on micelle flexibility, entanglement, and connectivity within the fluid. In Figure 6, detailed cryo-EM images trace the evolution of micellar morphologies at 16.7 millimolar CpYCl across increasing diclo concentrations from 7.3 to 12.5 millimolar. Panel A, with 7.3 millimolar diclo, reveals the early stage of elongated micelle growth. A low-density, broad-length distribution of rod-like and worm-like micelles is visible, ranging from tens to hundreds of nanometers. Panel B, at 10.5 millimolar diclo, corresponds to the viscosity peak, showing a tighter, denser micellar network with long worm-like micelles devoid of visible chain ends, suggesting a highly connected mesh. Panel C, at 11.5 millimolar diclo, demonstrates branching and increased micelle flexibility, with denser entangled networks exhibiting knots, loops, and overlap chains. Panels D through F, covering diclo concentrations of about 12 to 12.5 millimolar, illustrate the transition from branched micelles to perforated vesicles. These vesicles appear large and polydisperse, ranging from roughly 110 to 450 nanometers in diameter, existing alongside branched micelles. Taken together, these images support the idea that added salt screens electrostatic repulsion, promoting chain folding, branching, and eventually driving vesicle formation. The coexistence of multiple morphologies underscores a gradual, rather than abrupt, structural evolution, correlating well with the preceding rheology results and viscosity peak behavior. Moving on to Figure 7. The focus is on samples with higher CpYCl concentration at 33 millimolar and diclo at 19 and 20 millimolar. The frequency sweep tests reveal that these samples maintain characteristics typical of worm-like micellar networks. Both compositions exhibit well-defined plateau regions in the storage modulus and a distinct minimum in the loss modulus, indicating stronger entanglement compared to lower surfactant concentrations. However, with increased diclo, the micellar chains become more flexible, exhibiting knots, loops, and darker particles indicative of overlapping chain sections. This implies the micelles are less rigid, but still form entangled networks. The authors observe that this increased flexibility coincides with the onset of vesicle formation, suggesting a nuanced balance between entangled worm-like micelles and vesicular structures in these concentrated systems. These rheological findings add to the picture of salt and drug concentration-dependent modifications of micelle microstructure, highlighting how network topology evolves in surfactant drug solutions at high concentration regimes. Figure 8 presents cryo-EM images of samples corresponding to the previous 33 millimolar surfactant concentration experiments, with diclo at 19 and 33 millimolar. Panel A captures the sample at the viscosity peak, 19 millimolar diclo, displaying a dense worm-like micellar network that is visually more compact than in lower concentration systems. The worm-like micelles appear less rigid and more flexible, although this assessment remains qualitative. Dark spots in the images suggest overlapping chains, but distinguishing between true entanglements and branching points is challenging at this scale. Panel B at 33 millimolar diclo shows coexistence of large vesicular assemblies along with micelles, similar to lower surfactant concentration findings. This coexistence indicates the micelle to vesicle transition is gradual rather than abrupt. Thus, at high surfactant and salt levels, the structure evolves from flexible, entangled worm-like micelles with complex topology toward vesicular morphologies consistent with rheological data. These images reinforce the concept that charged drug addition modulates electrostatic interactions and structural transitions within surfactant solutions across concentration regimes. To conclude, this study systematically elucidates how surfactant concentration and charged drug addition govern the formation and evolution of micellar structures, linking them to rheological properties. The zero-frequency viscosity response reveals a characteristic peak that shifts with surfactant levels, marking key points of micellar growth and transition. Frequency sweep tests demonstrate classical worm-like micellar behavior at low and moderate surfactant concentrations, evolving to increasingly entangled, branched, and eventually interconnected micellar networks with higher surfactant or drug. Cryo-EM imaging visually corroborates these microstructural transformations, capturing morphologies spanning from sparse worm-like micelles to dense entangled networks, branched micelles, and perforated vesicles. Notably, the transition from worm-like micelles to vesicles is gradual, with coexistence observed over a range of conditions rather than abrupt. This work highlights the importance of electrostatic screening by charged drugs in modulating micelle flexibility, branching, and vesicle formation. These insights advance our understanding of surfactant drug systems and have potential implications for formulation design in pharmaceuticals and soft materials with tailored rheological behavior.